first thing I need to do is I need to tell you what all of those things mean. So we've been talking a lot about simplicial complexes today. Simplicial posets are like simplicial complexes, they're just a little bit different. So formally, a simplicial poset is a poset. It has a minimal element, and I'm usually going to think of that as being the empty set. And it has this property that all of the intervals from any element of the poset, from the empty set to any element of the poset is isomorphic to a Boolean lattice. And I'm going to think of these objects geometrically, and what we're going to do, it's graded. We can grade by however many elements are in that Boolean poset. And we're going to think of this geometrically by putting a k-1 dimensional simplex into some geometric object for each element of the poset. And the reason for that is that the face poset of a simplex is a Boolean lattice. Right? So this is where the connection is coming in. And because I prefer to think of everything geometrically, instead of talking about the elements of the poset over and over and over again, I'm really going to think of them as faces, and I'm going to identify the geometric realization of this simplicial poset as the poset itself. So I'm just going to call them one and the same thing, even though they're technically different. So let's look at an example. If this is my simplicial poset, I'm going to show you how to draw the geometric realization of it. So the first thing we do, the way I like to do, is start at the bottom. So we'll start by drawing the empty face, which you see right there. It's the only joke of the talk today. And then we move up to rank 1, and I have these three elements, A, B, C, of rank 1. Right? They're lower order ideal down to the empty set. Looks like a Boolean lattice of rank 1. And I'm going to insert vertices A, B, and C in my geometric realization, one for each element of rank 1. Now we can move up to rank 2. I'm sorry, this is difficult to see. This element of rank 2, its lower order ideal, looks like a diamond, so that's a Boolean lattice of rank 2. It covers the vertices A and B of rank 1, so what I'm going to do is I'm going to insert an edge that connects A and B. And similarly for these other two elements of rank 2, these are supposed to be blue and green. I don't know if you can see them that well, but this element covers A and C, so I'm going to insert an edge between A and C. And this guy covers B and C, so I'm going to insert an edge between B and C. But now, the way in which a simplicial poset differs from an ordinary simplicial complex is that I can throw in this one more element of rank 2 that also covers B and C. And what that means is that I should insert another edge connecting B and C over in my simplicial poset. So in simplicial complexes, you can't do this. In a simplicial complex, a face is entirely determined by its set of vertices, but in a simplicial poset, there's nothing wrong with it. So this is like relaxing the condition of having a simple graph to allowing multiple edges. And so now I'm taking a simplicial poset. Not only can I introduce multiple edges, but I can introduce multiple faces as well. And then once I get to the top, this is supposed to show the element at the top. It's rank 3. Its lower order ideal looks like a Boolean lattice of rank 3. So I'm going to fill in the space on A, B, and C. And just one thing to be careful of, I chose to include this element covering B and C, this edge that covered B and C of rank 2, and so that's why I'm putting my triangle on this frame instead of potentially on the one around the outside. So if we prefer to think topologically, a simplicial poset is a regular CW complex. All the faces are simplices, and I can have two simplices now that intersect along a collection of faces. So in that previous example, I had the two edges that intersected along two vertices, but not the entire complex. So faces can intersect along entire subcomplexes at their boundary. And for this reason, these objects are sometimes called simplicial cell decompositions. And that's used more as a sort of a descriptive phrase. So I might say I have a simplicial cell decomposition of a sphere, a simplicial cell decomposition of whatever your favorite topological space is. And just to really emphasize the contrast, a simplicial complex is a simplicial poset where you have a greatest lower bound property. So you have a meet property in terms of simplicial complexes. This just means that any two faces intersect in a face. For simplicial posets, that's going to fail. And so what do we want to do? Well, just like with the simplicial complex, in a simplicial poset, I can count how many elements are there in each rank. That's saying how many faces are there in this geometric object of each dimension. And we call those the F numbers, just like Iran and Jose were saying for simplicial complexes and simplicial polytopes as well. So we're going to count the F number of these objects, telling us the number of I-1 dimensional cells in the poset. And we define the H numbers of a simplicial poset in the exact same way as you do for a simplicial complex. Okay, they're defined as some alternating sum of binomial coefficients involving the f numbers of the poset. And just to emphasize this again, this formula that takes you from f numbers to h numbers is invertible. So if I know the h numbers, I know the f numbers. If I know the f numbers, I know the h numbers, going back and forth. And there's a good reason for this, and because this is a complex or a conference on formal power series, I feel like I should have at least one power series, and this is the only one. So it turns out that you can define a face ring for a simplicial poset, just as you would define a face ring for a simplicial complex. And the definition's a little bit more complicated. Instead of having generators corresponding just to the vertices of the complex, in simplicial poset land, you have to kick in generators for all of the possible faces, and then the relations that you mod out by become a little bit more complicated. I just want to say that such a thing exists, and it turns out that its Hilbert series is still a rational function whose numerator has those h numbers as its coefficients. So this definition still makes sense for good reason, other than just using the same formula over again. It's the simplicial poset. So what we want to do is we want to pick some family of simplicial posets and ask what can we say about all of their possible h vectors. Remember again, knowing f vectors and knowing h vectors is equivalent, and just like we saw in Iran's talk, Jose's, sometimes h vectors are just a little bit nicer to work with because we have this algebraic structure, because they encode nice symmetries, for example. So maybe we're going to look at all simplicial cell decompositions of a sphere, or simplicial cell decompositions of whatever your favorite manifold is, with or without boundary. Or we can look at two generalizations of these objects to what are called Cohen-Macaulay simplicial posets, or simplicial complexes, and then Buchsbaum simplicial posets and simplicial complexes. And I'm going to give you the formal working definition of this on the next slide, but what I'd like to say is that Cohen-Macaulayness is an algebraic condition. I'm not going to tell you what that algebraic condition is, except if you know it, it means that the face ring that I haven't defined has this algebraic property. But you can really think of it topologically instead. And Cohen-Macaulay simplicial posets and simplicial complexes, you can think of that as an algebraic generalization of spheres and balls. And Buchsbaum simplicial posets, those are going to be things that locally look like Cohen-Macaulay posets, and just like manifolds are defined in terms of being locally looking like a ball or a sphere, Buchsbaum simplicial posets are generalizations of that, so they're algebraic generalizations of manifolds with or without boundary. So when you see Cohen-Macaulay, think sphere or ball. When you see Buchsbaum, think manifold with or without boundary. And in order to make this idea of working locally and behaving like something else locally precise, we can define the link of a face in a simplicial poset. And what that is it's just the upper order ideal of all the faces that live above whatever this tau is that you're taking the link of. So in our example from before, if I want to take the link of vertex C or atom C, then what I'm going to do is I'm going to look at the upper order ideal. Is there any sense at all that there are colors there? Okay, cool. So I've got C, I've got the three edges that live above it, and it's also contained in this one maximal element. And if I want to view that as a simplicial poset, well now if I throw everything else away, C is my new minimal element. The rank 1 elements in this upper order ideal were the three edges that contained it, so I can think about that as just throwing a vertex down in the middle of each edge. And then this triangle that contained C, now I can think of that as just an edge connecting the two vertices in the middle of the edge. So if I throw away all that extra information, I can realize this as a new simplicial poset. And this is always true. If I have a Boolean lattice and I look at an interval in it, it's still Boolean. So links in simplicial posets are always going to be simplicial posets themselves. And really, like Jose was saying, in polytopes, if you want to look at the link by slicing really close to your vertex with the hyperplane, that's one way to think about it. Here, I don't really have that structure, but I can still think about taking a little epsilon ball near my vertex C, and whatever I intersect with, that's going to be what the link looks like. Okay, so what could we do now? If I want to define Cohen-Macaulay and Buchsbaum simplicial posets, remember those are my generalizations of spheres and balls, and manifolds with or without boundary respectively. You can either take this as a definition or a theorem that a simplicial poset is Cohen-Macaulay if and only if, when I take the link of any face, and this includes the empty one, I should get something that's acyclic in positive codimension. So it has no homology except potentially in the top degree. And what that top degree is if d minus 1 was the dimension of my original poset, and that means that it had rank d. If I take the link of something that has rank tau, my new poset is going to throw away everything below rank tau. So this d minus rank of tau minus 1 is what the right dimension of the link ought to be. And so all this is saying is that I don't have any homology except in top degree. And since I'm allowed to include the empty face in this scenario, taking the link of the empty face just means take everything that sits above the empty set in my poset. So that's just everything that was there originally. That means that on a global scale, this has to hold as well. So globally, I have to have homology that vanishes in codimension 1 and higher. So that's why, if I take spheres and if I take balls, they're definitely going to be Cohen-Macaulay, because locally, around any vertex or around any face, you'll see another sphere or ball, depending whether you're in the interior or boundary. And globally, spheres and balls have vanishing homology except in the top degree. And more generally, if you know what this means, any shellable simplicial complex is Cohen-Macaulay. And you can extend the notion of shellability, the definition of shellability, to simplicial posets as well. This was done by Bjorner, and those are Cohen-Macaulay, just the same. So going towards Buchsbaum simplicial posets, again, this is either a definition or a theorem, depending on how you define things. A Buchsbaum simplicial poset is one that's pure. So this just means that all the elevators go to the top floor. Every element is contained in something of maximal rank. And the link of every atom is Cohen-Macaulay. Now what this really means is the link of every non-empty face is Cohen-Macaulay as well, because links can be iterated over and over with one another again. So it's enough to say that the links of the atoms are Cohen-Macaulay, but this says nothing about the global structure of my complex. So it can have homology running around like crazy, but locally all the links have to be Cohen-Macaulay. So if you think again about the link as telling you local information, in a manifold all of your links should be spheres and balls, which are Cohen-Macaulay. So a manifold triangulation is sort of the canonical example of something that's Buchsbaum. But there are more. This is a much bigger class than just manifold triangulations or manifold cell decompositions. Okay. So, like I said before, our goal is you give me your favorite class of simplicial complexes, simplicial posets. For the purposes of this talk, it's going to be the ones that are Buchsbaum. What can we say about the H vectors? And what I'd like to convince you of on this slide is that in general, working with simplicial posets is easier from a combinatorial perspective than working with simplicial complexes. So the complexes are more structured. And the way we can see this is there are two results of Stanley. One says if you want to tell me what are the H vectors of Cohen-Macaulay simplicial complexes, they have to be M vectors. This was something that Aram was discussing earlier, but what this means is that I can find a corresponding family of monomials where the number of monomials of degree j is whatever my jth H number is. That has to hold for Cohen-Macaulay simplicial complexes. For simplicial posets, the only requirement is that these H numbers are non-negative. So for complexes, if I'm counting something, these H numbers have to be non-negative. But for posets, the only thing that has to happen is the H numbers have to be non-negative. There's nothing that tells you how they grow relative to one another. So for a Cohen-Macaulay simplicial poset, a perfectly acceptable H vector is 1, 0, 1, 0, 1, 0, 1. And that's okay. So there's a lot less structure. That means it's also easier to describe what these H vectors are. And for Buchsbaum posets, it turns out, I'm sorry, I forgot to say something. The reason why this M vector condition is coming along is that the H vectors are telling you something about taking the face ring of the simplicial complex, modding out by a system of parameters. So there's this algebraic reason running around in the background for the structure of the H numbers, and in particular, why they're even non-negative. For Buchsbaum simplicial posets, we want to take the right algebraic generalization of H numbers, and it turns out that it's not just the H vectors. So this was something Aram was discussing as well. What we want to do is we want to consider these things that are called the H prime numbers. And the way we get these is we take the dimensions of the homology groups and we kick in the H number that we started with before together with some alternating sum of Betty numbers. If if you want sort of the most naive reason that we're doing this, it's that the H numbers of a Buchsbaum simplicial poset may not be positive, and that's not good. But these H prime numbers turn out to be the dimensions of the graded vector space that you get when you take the face ring of a Buchsbaum simplicial poset and you mod out by some system of parameters. So these are nice non-negative numbers, and they serve as the right algebraic generalization of the H numbers. So if we go back to our Cohen-Macaulay definition and we look at this formula for a moment, one thing to notice is that when I'm taking the jth H number, the index on the top here goes up to j minus 1, and I'm considering then the I minus first Betty number. So even when j is d, the largest Betty number that I'm going to be considering on the right side here is d minus 2. So in the Cohen-Macaulay case, remember, if I'm d minus 1 dimensional, I'm acyclic and positive codimension, so all of these Betty numbers that I care about are 0, which means that the H number and the H prime number are the same for Cohen-Macaulay complexes. That's good. Again, the right algebraic generalization. And one more thing, in case you've seen this before, and if you were at Iran's talk, you did. It turns out that the top H number of any simplicial poset is its signed Euler characteristic, plus or minus. And so if we then look at this formula, when j is d, these binomial coefficients are d choose d, they go away. And so I'm taking the Euler characteristic and adding or subtracting off the sum of the Betty numbers. It turns out if you chase the signs around in the right way, they all kill one another except the top one, the Betty d minus 1 that doesn't show up. So it turns out that the top H prime number, instead of being the signed Euler characteristic, is just whatever the top Betty number is. And that's going to be useful on the next slide. So if we remember, so here for Cohen-Macaulay simplicial posets, the only real requirement we had was that H0 was 1 and the rest of the H numbers were non-negative. So the question now we want to answer is, what about Buchsbaum simplicial posets? And Isabella and Ed, or Novak and Swartz, showed that if you have a Buchsbaum simplicial poset, then not only are these H prime numbers non-negative, which I sort of alluded to because they're telling you the dimensions of some graded vector space, but also they're bounded from below by a binomial coefficient times a Betty number. So the homology groups are showing up here somehow. Okay, oh, it's right there. And again, this is a generalization of Stanley's result, because in the Cohen-Macaulay case, the H prime numbers and the H numbers agree. So here, for Cohen-Macaulay complexes, we're getting H numbers, and again, the Betty numbers all vanish, so we're getting zeros. So this is again telling us that the H numbers of Cohen-Macaulay complexes are not negative. And so we can ask, is this enough? Is this inequality essentially enough to characterize the H prime numbers of Buchsbaum simplicial posets? And we need two technical conditions. One is, again, that the first H number is always going to be 1, and then based on that calculation that I just showed you, the top H prime number has to be exactly the top Betty number, whereas if we just look at this formula, when j is d, this would say H prime is at least the top Betty number, and we need equality. So these two things are technical, but essentially we're asking, is this enough? Is it enough that if this inequality holds on all levels, that there is a Buchsbaum simplicial poset with those prescribed Betty numbers and H prime numbers? And what I want to tell you is that the answer is yes. And there's one key reduction that Novak and Swartz did, and they said, if you want to prove this, if you give me Betty numbers and you give me H prime numbers that satisfy this inequality, and you want to construct a Buchsbaum simplicial poset with those H prime numbers and Betty numbers, it suffices to reduce to the case that you have non-vanishing homology in exactly 1 degree, which is easier to handle than non-vanishing homology all over the place. And second of all, it's enough that you consider the case where equality holds here. So that's what this big mess is saying. It's saying that I have non-vanishing homology exactly in degree k, and then this is saying that the H prime numbers are that binomial coefficient, which is 1 times the Betty number. I'm sorry, d choose j times the Betty number of 1, when j is 0 or k plus 1. So j being 0, again, that's just saying that H prime of 0 has to be 1. That's a technical condition. But this is saying that it's enough to consider the case that there's one non-vanishing Betty number and that equality holds everywhere here. The reason why that's the case is that if I can construct these objects, I can glue them together, just identify them along a top dimensional face. It turns out that process is additive on both homology and H prime numbers, which is good. So that gets me the case where equality holds everywhere here. And then if I want to move away and go up to inequality, I can take a Cohen-Macaulay complex that sort of makes up the difference and add in on as well. But I'm being very fast and loose here in the interest of time. And we're going to call this complex XKD. I couldn't get a C in there. But we're calling it XKD, where K is standing for the homology, where things are vanishing, and D is standing for the rank of the poset. And so what I'd like to do is I'd like to tell you how we do this. Sorry, so that's what we did. We constructed these objects for all K and all D. Just for some examples, when K is 0, I'm not going to convince you that these are the right H numbers. I want to give you some idea of where you might look for such things. When K is 0, we want something with non-vanishing 0 homology that's pure. So that's got to be 2 disjoint simplices. When K is 1 and D is 3, now we're looking at something that's 2-dimensional, and it has non-vanishing homology only in first degree. So morally, in the back of your mind, you should think it's a disk bundle over a sphere. And it turns out the cheapest way to do this is to take 3 triangles, stack them together, and then identify the opposite sides with a twist. And we do it with a twist just so that these vertices line up. The reason why we can't do it without a twist is that if both edges pointed this way and we did the gluing, this edge would become a loop. And even though we allow multiple edges, we don't allow loops. So we get this Mobius strip. And then if we go all the way up to the top, when K is D minus 1, if we want something that has non-vanishing homology only in top degree that we can construct sort of as cheaply as possible, the way to do that is to take 2 simplices and just glue them entirely along their boundary together. Hopefully you agree with me that that's at least a sphere and that it's pretty small. So the main tool that we used in order to construct these things, right, there seems to be a lot running around here. We've got to understand the homology groups of these objects, then we have to check that they're Buchsbaum, and then we have to check that they have the right H prime numbers, which means that they have the right H numbers, which means that they have the right face numbers. So there's a lot, it seems like there's a lot to do. And the main thing that we did in order to make this construction work was we used the theory of crystallizations, and we extended it a little bit. So the manifold crystallizations are things that have been studied by other groups before. The way you want to think about this is it's a generalized dual graph. So on the left here I have this graph. Its edges are labeled by the numbers 1, 2, and 3. And it has 3 vertices, which I've decided to call capital A, capital B, capital C. And there's a corresponding simplicial poset that I'm going to build on the right-hand side here, where I have one facet, A, B, C, for each of the vertices in my graph. So again, it's a generalized dual graph. And now, since I have a simplex in each case with 3 vertices, I can number them sort of arbitrarily as 1, 2, and 3. And now this edge, so for example, this edge colored 1, this edge between A and B that's colored 1, inside facet A and facet B, they each have a vertex that's colored 1, and there's a ridge that's opposite that. So what this edge labeled 1 means is that I take these 2 opposite faces and I glue them together. The same thing for the edge 3 between facet B and facet C. There are edges in each one that's opposite the vertex colored 3. I glue them together. And then this last one, from A to C, I look at the edges opposite vertex 2, which has already been glued together, and I glue them. And again, I'm identifying colors at each step along the way. So this simple graph encodes that Mobius strip that we've already seen. It turns out this generalizes to all dimensions, right? If I take a dual graph, and instead of labeling its vertices 1, 2, and 3, I can label them 1, 2, 3, yada, 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 up to D. This is going to give me a generalized dual graph for simplicial posets of rank D. And also something I haven't shown you here, there's no reason that I have to restrict attention just to having one label on each edge. I could have an edge labeled 1 and 2. And geometrically, the way you can think about that is now I have two triangles. They each have edges opposite vertex 1 and vertex 2, so that's two of them, and then I'm going to make a little pita pocket where I glue these two edges together at the same time. And again, this is not a simplicial complex property anymore, but it's perfectly legit for simplicial posets. Okay, so here's what we do. This is how we build up this generalized dual graph for Buchsbaum simplicial posets. What we're going to, I just want to skip ahead. Can anyone see this at the bottom? How about on this side of the room? No. Okay. So I'm going to draw this alongside. So we're going to build up this generalized dual graph. And the vertices, to begin with, they're going to be labeled by 0, 1 words. So words of length D, where each letter is 0, 1. They have to start with a 1, and they have to have k plus 1 blocks of zeros and ones. So blocks just meaning 0, 0, 0, and then you switch and you have some ones, and you switch and you have some zeros, blah, 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 blah. So if we're going to build x of 1, 3, this means we have words of length 3. They have 2 blocks of zeros and ones, and they start with a 1. So there are only 2 such things. They're labeled 1, 0, 0, and 1, 1, 0. The next thing I'm going to do is I'm going to say if I have 2 of these vertices, if they differ only in their ith letter, I'm going to put an edge between them labeled I. So here 1, 0, 0 and 1, 1, 0, they differ in their second letter only. So I'm going to put an edge between them, and I'm going to label it 2. And now I'm going to do one more thing. So we know, we've seen x13, it's a triangle where the edges are labeled 1, 2, 3, and this is not it. So I need one more thing, and what we're going to do now is we're going to add an extra vertex. And we call it alpha. We think about this as like a vertex out at infinity somewhere. And the rule for adding alpha is that alpha gets connected to any of my other vertices if flipping the ith bit in this vertex decreases the number of blocks. So my rule before was that all of these vertices have to have k plus 1 blocks. So now if that number goes down, when I flip the bit, I'm going to add one more edge. So like with 1, 0, 0, if I flip the first bit, I get 0, 0, 0. That only has 1 block of zeros and ones, which is unfortunate. So I'm going to put an edge labeled 1. Similarly with 1, 1, 0, if I flip the third bit from a 0 to a 1, my word becomes 1, 1, 1. That has 1 block. That's too bad. So that gives me. So it works in this case. And it turns out that this always works. There are some things we have to do in order to show that these objects are Buchsbaum. We have to show that their links are Cohen-Macaulay. It turns out that you can do a lot of this stuff in terms of the dual graph. You can count the face numbers in terms of the dual graph. We can understand the links in terms of the dual graph. We show that the links are all shellable, which is how we prove Cohen-Macaulay, so we don't have to do any homology calculations, which is nice. And we can interpret the H numbers of all of the links in terms of the graph, and from there we can get to the global H numbers straight away. So I think one thing that's cool is that we did this entire thing without doing a single homology calculation. It all just follows from the numerics of how things fit together. One unfortunate thing is that if we go to x25, I don't expect you to read through this entire construction, but this is a picture of what the dual graph looks like. I've just drawn vertex alpha 3 times, so it's nice and planar. If you look at these 4 vertices at the bottom, what this tells me is that in vertex alpha, there's a ridge opposite vertex 5. It intersects 3 other facets. That's what these 3 edges labeled 5 mean, which means that this thing isn't a manifold, because you have a ridge that's contained in 4 facets instead of just 2. So the question I'd like to know is, when can we do this as a manifold? So Jonathan and I proved that when k is big, it's impossible to realize these objects as manifolds. The numerics just don't work out. None of our simplicial posets are manifolds except the one like this that's a Mobius strip. and the other one that I told you where you get a sphere by gluing two simplices together along their common boundary. But Novick and Swartz came up with a construction where you take a minimal decomposition of CP2 and pop one of its facets out, and that works. So what can you do? You can come up with manifolds in general when K is small. And with that, thank you all for your attention.
Any questions for Steve?
It's almost a shame to mess with the Cohen-Macaulay calculations. It's so simple, but I can't resist. So there's the idea of sequential Cohen-Macaulay transforms non-pure. Is there a characterization in that case?
I don't know. I can't remember if there's anything in Andres' paper. I don't recall.
So in the cases where you construct with the Mobius strip or the other, can you also do it with oriented, right?
No.
So it's impossible.
And the reason why is this has the right F factor, unfortunately. You only have